Welcome to part 2 of this video on limits of complex functions. So in this second part of the video, what we're going to do is look at the rigorous definition of what a limit means in complex analysis. So I'm going to start by writing down this definition and then we'll explore what it means in more detail. So firstly, let me just write down our general limit then. So the limit as z approaches z0 of the function f of z is equal to L. So all I've done here is introduce some new notation so that we've got our general limit so that we can define what this means. So we've got our function f of z here. We're taking the limit of our function as z approaches some value in the domain, and all I've done is introduce a name for that general point. z0 is just the value in the domain that we're taking the limit of the function of as z approaches that value. So nothing complicated there, I've just introduced a piece of notation, and L is simply the piece of notation that we've introduced to mean the value, the complex number in the codomain that the limit is equal to as z approaches z0 of this function f of z. So what we now want to say is, what does this actually mean then? So this limit that we've got here, if this is true, what is the rigorous definition of what that actually means? So here we go. So I'm going to write this down. It is a bit of a mouthful. We'll explore what it means after I've written the whole thing down. So what this rigorously means then is, for all epsilon greater than 0, so epsilon is a real number, so it's a positive real number, so whatever positive real number you take, and we're going to call that positive real number epsilon, there must exist, if this statement is true, there must exist a delta, which is also a positive real number, so a delta greater than 0, such that for all complex numbers z that are elements of the deleted open ball centered at z0 of radius delta, and don't worry if you don't know what a deleted open ball is, I'll explain in a moment, f of z, so if you take the value of that complex number once it's been mapped by the function, it is going to be an element of the open ball, this time not deleted, centered around the limit L of radius epsilon. So there you go, that's a bit of a mouthful. This is the reason people don't like analysis. The first thing to do is just to explain what open balls, closed balls, and deleted balls are, and then we'll examine what this statement is actually saying, and it really is not as difficult as it looks. So let's start with, what does an open ball mean? So if I write this terminology, an open ball, B means open ball, centered at Z0, of radius, let's just say R, what this means in the complex plane, so I'll just draw a picture of the complex plane, is it's a subset of the complex plane, and it includes all the points within a radius of R of this point Z0. So I'm just drawing on my picture Z0 here. So this is just our complex number Z0 that we're centering this open ball at. We're using the same notation for this point as we use over here. Because obviously we have an open ball centered at Z0 here, so it made sense to use this notation again, but I could have changed this, I could have called our complex number anything. So if we have an open ball centered at a complex number of radius R, what this means is the set of all complex numbers that are within a radius R of that point. So it means effectively this little circle of complex numbers around Z0, where this circle is radius R. So to write that down in set notation, this is all the complex numbers z, so z is going to be a complex number, such that the distance between z and z0, so if you take z minus z0, you'll get another complex number. If you take the modulus of that, you'll get the length of it, is going to be less than r, and it's strictly less than. So importantly, on this picture, it does not include this boundary. So the complex numbers that are a distance r away from z0, i.e. are on this circle here, those are not included in the open ball. If we talk about closed balls, and to make this the closed ball, you put a bar over the B like so. So if you see the notation with a bar over, that means the closed ball centred at z0 of radius r, that would then include the boundary. So the definition would still be this: all the complex numbers in the complex plane such that the distance between that complex number and z0 is less than or equal to r would be the definition if it was a closed ball. So you'd make this less than or equal to. But we're talking about open balls here, so we don't want the boundary included, so we want strictly less than r. Finally, what do I mean by b apostrophe z0 delta like this? This means the deleted open ball. And that means that you do not include the point itself. So when we had open balls previously, and imagine that that bar is now gone. In fact, I'll rewrite it out. So we're not interested in closed balls here. We're actually just interested in open balls. So we want the open ball centered at z0 of radius r. Remember, that included all the complex numbers that were within this circle of radius r around z0. So it included z0 itself. So this set had all of these complex numbers, but it also had z0 itself in there. When we're talking about deleted open balls, that means include all the points that are within a radius r of z0. However, do not include the point z0 itself. So, if I wanted to write that down, I could say that the deleted open ball around z0 of radius r, it's the same thing as the open ball around z0 of r. It's the same set, except that you take out one point, and that point is the centre of the open ball itself. You take out z0. So that's what we mean by deleted open ball. Now, there are other names for these. You can also call an open ball an open neighbourhood. So you could call this the open neighbourhood centred around z0 of radius r. You could call this the closed neighbourhood around z0 of radius r. And you could call this the deleted open neighbourhood around z0 of radius delta in this case. And of course you could also have the closed deleted the closed deleted neighbourhood around z0 of radius delta. We're not interested in that, but you could have it. So you can either call these balls, you could call these discs in the complex plane, because after all they're not going to be balls here, they are discs, or you can call them neighbourhoods. Neighbourhoods is very fitting with the terminology that's used in topology, but they're all meaning the same thing. You can use whichever one. So now that we have discussed that notation, let's now discuss this definition, because we understand all of the notation now. It's just understanding what this actually means now. So the best way to do this is to draw a picture. So let's just move down a little bit and draw this picture. So we need to draw a picture of our function. We need to draw a picture of our domain and our codomain and the function going between the two. So let's start by doing that. So here is our domain, here is our codomain, and we know of course that the function is a mapping from one to the other. Let's now add on to our picture the point z0, so we'll put that here, and let's add on to the picture of the codomain over here the point L, the limit value. Let's also add on these open balls that we're talking about here. So let's add on the open ball around the limit L of radius epsilon, and let's add on the deleted open ball around the point z0 of radius delta. We don't know what epsilon and delta are, but we do know that they are positive real numbers, so we can draw these pictures to get some idea. So let's start with the open ball around the point L of radius epsilon. So here we go. This can represent it, and that's going to be of radius epsilon, that disk here. And that was an open ball, so it included the point L at the centre. It wasn't the deleted open ball. Let's now draw the deleted open ball around the point z0 of radius delta. And again, we don't know the exact value of delta. It doesn't matter for the purposes of the picture. The picture is just to give us intuition. So the radius of this is representing delta. And of course, that was a deleted open ball. So to remind ourselves of that fact, we'll colour the point z0 in red to remind ourselves that that is not included in that deleted open ball. So I might just label these up. That is representing the deleted open ball around the point z0 of radius delta, and this is representing the open ball around the point L of radius epsilon. Brilliant. So we now have our picture and we are ready to actually take on this definition. So let's just move up so that we can have the definition in full sight. So let's think about what this means. So if this statement is true, if the limit of the function f of z as z approaches the point z0, which is here in our picture, is indeed equal to this value L, this is what that means. It means, rigorously, that whatever epsilon you give me that is greater than 0 for absolutely all of them, which means that for absolutely all of these open balls around the point L of radius epsilon, there must exist a delta that is greater than 0, so there must exist one of these delta balls around the point z0 such that for all the complex numbers that are in that deleted open ball, so all the complex numbers that are an element of this set here, when you take what they are mapped onto by the function, it must be within the epsilon ball. So let's say that again. What this is saying is, if L is truly the limit of the function as z approaches z0, then you have to be able to take all of these open balls around L, so whatever radius you give me, I can construct an open ball around L of that radius, and you have to be able to find a corresponding open deleted ball in the domain over here, centered around z0, such that all the points in there are being mapped into that ball. Let's say that again in a different way. Think what the limit intuitively means. Remember the intuitive meaning of the limit. The intuitive meaning of the limit was that as you get closer and closer to the point z0 in the domain, the points in the codomain that those points in the domain are mapped onto by the function are getting closer and closer to the limit. That's what it intuitively meant, remember. We were a little man in the domain walking closer and closer to the point z0, and we were looking at what the value of the function for those points really close to z0 were, and they were getting closer and closer to the limit L, and that is why we made that guess that the value of the function at z0 would be L. Remember, that was the intuitive meaning of the limit. What are you getting closer and closer to as you get closer and closer to the point z0? Not what is the value of the function at z0, what are the values getting closer and closer to? What this definition is saying is no matter how arbitrarily close you get to the point L, I can always find you points that are really, really close to z0 that are all within that open neighborhood around L. So remember, I can make epsilon absolutely tiny. You can make this epsilon ball around L ridiculously tiny. And this definition is saying that you must be able to find an equally tiny little open neighborhood around the point z0 such that all those little points in that tiny little neighborhood around z0 are being mapped into that ridiculously close neighborhood around the limit. So this is effectively saying exactly what we intuitively thought of the limit meaning. It's saying that the points over here, as you get closer and closer to z0, are getting arbitrarily close to the limit. That's all it's saying. And because this is complicated, I'm going to go over it again because it's really, really important that you understand it. Intuitively, if we were trying to write a rigorous definition of a limit, what we want to happen is we want to say, no matter how close we get to this limit, you are going to be able to find a point or a neighborhood, a bunch of points around the point z0, such that those points are all going to be mapped into that proximity to L. And that's what this definition is saying. It's saying no matter how close we get to the limit L, no matter how small you make this open ball, if it is true that the function is converging to this limit L as z approaches z0, that means that you must be able to find me a corresponding tiny little delta ball, and you can make this delta as tiny as necessary. It doesn't specify how small, how large the delta has to be. You can make it tinier and tinier and tinier, but if it is true that the function converges to L as z approaches z0, then you must be able to find a delta small enough such that if you look at the points within that radius delta around z0, and of course we don't include z0, that's the reason we have this deleted open ball, because of course, going back to our example up here, it might be the case that z0, as in the case of 0, was mapped somewhere really stupid. That's why we don't include the point z0 itself, because it might not be anywhere near the limit, as indeed our example before was nowhere near the limit. However, the meaning of the limit is that the points really close to z0, they all get really, really close to L. So again, let's say this again. No matter what epsilon you give me, if this is true, then for all the epsilons greater than 0, you can create an open neighbourhood of radius epsilon around L, and it categorically must be the case that you can find a little delta, and you can make delta as arbitrarily small as you need be. You can't make it 0, obviously, but you can make it arbitrarily, infinitesimally small if you need to. You make it really, really small, but you must be able to find such a delta such that if you look at that deleted open ball around z0 of delta, all of the points in that little open ball, and this is obviously our picture of this deleted open ball around z0 of delta. I resent this picture a little bit because it's quite big. I would prefer if it was tiny. In fact, I might just modify it. Let's say we're going to make it absolutely tiny around there, so that tiny little thing. And of course, remember, it doesn't include the boundary. I should have drawn it in dashed lines more ideally, but we can find a tiny little ball such that all the points inside that little ball, apart from z0 itself, because we've deleted that out, they are going to be mapped into the epsilon ball. And it's not necessarily a bijective map, not in any sense. It's just that all of these points in here have to end up in points in here. I'm not saying that it's an onto map. There will be points potentially in the epsilon ball that don't have a point here being mapped onto them. What's important is that all the points in the delta ball are being mapped into the epsilon ball, and you must be able to do that for all epsilon that is greater than 0. And even though that seems really complicated, it isn't. All that is capturing is this idea that the points in that neighbourhood of z0 as you get closer and closer to z0, they're getting closer and closer to L. So all this is saying is that no matter how close you want me to be to L, I can always find you a close enough neighbourhood to the point z0 such that all those points in the neighbourhood of z0 are being mapped into that proximity of L. That's what it's really capturing. It's saying that as you converge on the point z0, the points in the neighbourhood of z0 are getting arbitrarily close to the limit L. Now, if no such L exists, such that this is true, then of course we get to say the famous line from Mean Girls, the limit does not exist. So, just to finish with then, I want to summarise what we've seen in this video. So let's start by going over the intuitive definition of what a limit was, and then we'll again recite off that rigorous definition. So remember, the intuitive definition of the limit is as you approach this point z0, if you imagine being a little man, in fact we'll go down to our other picture. So the intuitive definition is as you approach z0, so if you imagine being a little man in the domain here, and you're approaching z0, getting closer and closer and closer, and you're studying all of these points very close to z0 are mapped onto in the codomain. As you get closer and closer to z0, you start to notice potentially a pattern in these values in the codomain that the points in the domain are being mapped onto, and you make a guess at what you are converging to, and from that you make a guess of what this value of f of z is going to be. So by looking at all the neighbouring points in the domain, what would you expect the value of f of z0 to be in the codomain? That is what the limit is all about. The rigorous definition then is that no matter how close you get to the limit L, if it's true that this statement is true, if the limit of f of z as z approaches z0 is truly equal to L, what that means is you must be able to draw an arbitrarily small open ball around L. That's what this epsilon is all about. You can draw an arbitrarily small open ball around the limit L, and you can then find an open ball around the point z0 of radius delta, such that all the points in that open ball, except for z0 itself, which is why we've made this a deleted open ball, because z0 could have been mapped onto something really stupid. It doesn't matter as far as the limit is concerned. All of those points are going to be mapped into that arbitrarily small open ball. You must be able to find such an open ball around z0 that is mapped into there, if it is true that the function converges to L as z approaches z0. You can make this as small as you need to be, but you must be able to find one. It doesn't matter how small you have to make it, but it must exist. And that is what this means. For all epsilon greater than 0, you must be able to find a delta. There must exist a delta such that for all the complex numbers that are in that deleted open ball around z0 of radius delta, they are being mapped into this open ball of radius epsilon around L. Thank you for watching. Actually, I would just like to do one final thing, which is just go back to our concrete example above and show you how the definition that we've just looked at for a limit holds true with this example. So remember, our example was this function f of z where it sent the complex number to z plus I plus 1 for all complex numbers apart from 0, and then it sent 0 to negative 3. And remember, we said that the limit of the function as z approaches 0 was equal to I plus 1, despite the fact that the value of the function at 0 was equal to negative 3. So let's now see how this definition here holds true in this case. So in this case, the limit is obviously I plus 1, z0 is obviously 0. So on our picture, up here in the codomain, this is the limit here, I plus 1, and we need to be able to prove that no matter what epsilon ball, no matter what open ball you construct around the limit L, so no matter what epsilon ball, and in fact that's a piece of notation or a piece of terminology that we use often when talking about limits, epsilon balls, we can call these things, just an open ball of radius epsilon. So no matter what epsilon ball we construct around the limit L, you have to be able to construct me a delta ball, which is what we'll call this, around the point z0, which is 0 in this case, such that all those points are being mapped into the epsilon ball around L. So, on our picture, we'll just let this rather conveniently drawn blue ball here represent the epsilon ball. Of course, it has a solid boundary there, which would usually represent a closed ball. So imagine that that is a dashed line. Remember, it doesn't include the boundary. So that's representing our epsilon ball. So for whatever radius epsilon ball I create around this limit L, I plus 1 here, I have to be able to create a delta ball, and we can just use this blue ball around 0 here to represent our delta ball. So this is of radius delta, such that all the points inside that delta ball, and I'll just colour those in, so all these points inside the delta ball, excluding of course the actual point z0 itself, remember it's a deleted open ball, so we don't need 0 itself to be mapped into the epsilon ball, we need all of those points to be mapped into our epsilon ball, and we have to be able to find such a delta for whatever epsilon you give me. Now of course in this example it's really, really easy. So if I set epsilon here to be equal to 1, for instance, I would need to be able to find a delta ball. And of course I can quite easily here set delta equal to 1, because if I look at this delta ball of radius 1 here, which is exactly what we drew in our initial example here, all of these points, excluding the complex number 0, they're going to be mapped into that epsilon ball of radius 1 here, because they're all being mapped according to this, and that was what we had originally drew here, this unit ball that was being mapped onto the unit ball over here. Of course, we're not including the boundary. We could have included the boundary because, frankly, it's working perfectly well, but as far as this definition is concerned, it doesn't need to include the boundary. But all of those points there are going to be mapped onto their corresponding points over here, so they are going to be within that epsilon ball. So for epsilon is equal to 1, we've perfectly satisfactorily found a delta that works. And that's why it's so important that this is a deleted open ball, because you see that point 0, that didn't work at all. That was being sent to -3, so that wouldn't have been in the epsilon ball at all. But it doesn't matter that the actual point that we're taking the limit as we approach is being sent to something stupid. That doesn't need to actually converge to the limit. It's all the neighbouring points that need to. Now, let's take another epsilon. So if we had set epsilon equal to 0.5, hopefully you realise that we could have set delta equal to 0.5 easily as well. Or we could even make delta smaller. We could have made delta equal to 0.3 for 0.5, because if we made a ball of radius 0.3 around here, that would certainly be mapped into an epsilon ball of radius 0.5. But why would we need to do that when we could have taken delta equal to 0.5? So hopefully it becomes reasonably obvious then for you that no matter what epsilon you take in this example, you just set delta equal to exactly epsilon, which is why this is such a nice simple example. So clearly, in this case, no matter what epsilon ball you create, no matter what epsilon is greater than 0 you pick, for all of them in fact, you can find a delta greater than 0. Quite simply, you set delta equal to epsilon, such that if you construct that deleted ball of radius delta around the point 0, which is z0 here, all of those points in that deleted ball are being mapped into the epsilon ball around the limit I plus 1 here. So that's a really, really simple example of how you can prove that no matter what epsilon greater than 0 you pick, no matter what epsilon ball you pick, you can find a delta ball. Obviously, in other examples, it's much more complicated to prove, but that's the basic gist of what you're trying to do. For no matter what epsilon ball you construct around the limit, you need to be able to find this delta ball around the point z0, not including z0 itself, such that all those points in that delta ball are being mapped into the epsilon ball. And it doesn't matter how small you make the delta ball. That's why I did this example where we could have set delta equal to 0.3, even though the epsilon was 0.5. You could make this arbitrarily small. You could have made it 0.1, 0.001. It would have still met this definition criterion for epsilon is equal to 0.5. It would have done the check for epsilon is equal to 0.5. So you can make the delta ball arbitrarily small, but you must be able to find one such that it is mapped entirely into the epsilon ball around the limit L for whatever epsilon you pick. That is what this definition says. Thank you.